In this video, I am going to explain dynamic characteristics of SCR. In this dynamic characteristics of SCR, we are going to see both turn on and turn off of SCR. Turn on timings and turn off timings of SCR. In the last video, we have seen the static characteristics of SCR. So, static characteristics means VA characteristics of SCR. We already seen that. Just I will draw it once again. Here, look at this. So, this is our anode current. This is voltage applied across the anode and cathode. So, after applying the anode voltage across device, then we are getting characteristics like this for SCR. So like this we have the characteristics with the forward bias condition, and in the reverse bias condition we have the characteristics like this. As for understanding purpose I am giving here, and whenever we apply gate voltage we are getting the conduction earlier than these voltage values like this. This we can say where Ig equal to 0. This is Ig1 I am calling, Ig2. So here Ig2 is greater than Ig1 is greater than Ig. Like this we already discussed about the static characteristics of SCR. The behavior of SCR we can see in the three types of characteristics. First one is static characteristics, second one is dynamic characteristics of SCR, and third one is gate characteristics of SCR. So we are at the second position, second characteristics. Now we are going to discuss the dynamic characteristics of SCR. Look at this. This is a simple diagram to explain the dynamic characteristics. So they are taking the structure of SCR, PN. This is M. Okay. So this is my anode terminal, this is my cathode terminal, and this is the gate terminal. Let us see the, suppose when we apply the forward bias to the SCR, what will happen? When we apply the forward bias, we will see them the turning on methods of SCR after continuing this, this characteristic continuously. But we should know how it is going to be coming into on state from its forward blocking state. Okay, so turn on process, turn on timings. Look at this. These are the characteristics, and this x-axis is timing. Look at it very carefully. X-axis is time in seconds. This also time, all are in time. And when we go for y-axis, the first one is gate voltage. This is gate voltage. And second one is voltage applied across anode and cathode. Voltage applied across anode and cathode. And these characteristics are the current flowing from anode to cathode. IA, what we call it is IA, anode current. Current flowing from anode to cathode. And third one is I am taking power loss due to the device using in the operation, in the circuit configuration. What will be the power loss occurring during the on period and off period of the SCR of the device? Okay, we will see on period. See, look at this. There are three timings that we can see for the on period of the on timings of the SCR. We can say those are, I am writing here. Look at this. T on. T on is equal to the summation of TD plus TR plus TS. So on time, which associated with the three timings, TD delay time, TR rise time, TS straight time. These three timings, after these three timings only our SCR comes into conducting state. Okay, we will discuss very deeply about these timings. Okay, look at this. It's very easy to understand all these timings. Very carefully. Whenever we apply the voltage across device, so 100%, let us take it is a 100% voltage is applied across the device. So if we are applying some duration of time, until some duration of time, some amount of leakage current will be flowing here. Look at this. Some amount of leakage current is flowing due to the magnetic carriers in the device. So magnetic carriers in the sense, if p-type material is there, magnetic carriers are electrons, majority carriers are holes. If n-type material is there, majority carriers are electrons, magnetic carriers are holes. Due to magnetic carriers in both the layers, both the p-type material and n-type material, creates some currents in the device. If the voltage is like this, means some leakage current is flowing through the device, which is a negligible value. But we have to mention here in the graph. So after that, what happened is, then our voltage is going to be reducing from its maximum value to the 90% of its value. Then during that timing, what during the duration, then our anode current is rising from leakage value, means 0 value to the 10% of its maximum value. So means this current anode voltage is going to be reducing from 100% to 90% of its maximum value. Anode current increasing from 0 value to the 10%. The time taken to increase anode current from its 0 value to the 10% of its maximum value is called delay time. Am I clear? Am I clear here? Look at this. We can define the delay time in other words also. Look at this in terms of anode voltage. When the anode voltage is going to be fall down from its maximum value to the 90% value, we can say that the time duration is delay time. Look at this. This is the delay time duration. Delay time duration. See this? Before the delay time duration only, we are applying gate signal. This is my gate signal. This I am calling IG. This is IG, this is VG. VG is always a constant DC supply that I am applying across the gate and cathode terminal. But our current is going to be increasing. Suddenly, like resistance is kept in between the gate terminal and the source. That's why it's having the linear character, thereby increasing like this and getting constant value. Then after that, as I said, delay time defined as when the current, anode current increasing from 0 value to the 10% of its maximum value, we can call the time is delay time. After that, what happened? This anode voltage is going to be fall down from 90% of its maximum value to the 10%. During that period, our anode current is increasing from its 10% to 90%. Vice versa. Means if voltage is going to be fall down, our current is going to be increasing. Means what? If the voltage is maximum across the device, indicating that our device is in forward blocking condition. What are the three modes of operation for the SCR? Three modes of operation are forward blocking mode of operation, for conducting mode of operation, and reverse blocking mode of operation. So on state means we are discussing two modes of operation. Those are forward blocking mode and conducting mode. Still our device is in forward blocking mode only. Look at this. So whenever the voltage fall down from its 90% to 10%, and as soon as the voltage fall down, our current is increasing. The current flowing through the device is increasing from its 10% value to the 90% value. That indicating there is a rise. There is a rise in current flow through the device. That's why we call that timing is rise time. Rise time is defined as the anode when the anode current reaching to 90% of its maximum value from the 10% of maximum value is called the time taken to anode current to reach the 90% of maximum value from its 10% is called rise time. So it can be defined in other words in terms of anode voltage also. The time taken by the anode voltage to fall down to 10% from its 90% is the maximum value is also called rise time. After that, look at this. During this position, what happened here? Okay, look at the diagram. Look at the diagram. See, whenever the gate supply is applied to device and forward voltage is applied across the anode and cathode. So, our main motto is anode current must be flow through the device. That is the main current. Okay, and we have the junctions J1, J2, J3. Three junctions, three terminals, four layer devices, our SCR. In that case, what happened? Junction J1 is forward biased. This is in forward biased condition. This is also in forward biased condition. But whereas our J2 is in reverse biased condition. So to flow the anode current, what happened? This J2 junction must be breakdown. This is the depression layer is there to stop the current to flow through the device. Then what we have to do is we have to break down this device. That is our aim, to make the current flow through the device. Okay, for that what we are doing is, so we are applying gate signal here and current is flowing. As I said, initially when you apply the voltage across anode and cathode, some leakage amount of current flowing through the device like this. See this? See this? The portion that I am drawing here, this is the portion that the leakage current is flowing. And same in the same time, gate current is also flowing like this. Means this portion, this entire portion is covered by gate current, and this is on the portion covered by anode current. Now what we have to do is we have to spread out the current flow entire the device like this, like this. So initially when the delay time occurring, because of the reason, because of the reason it's going to be that the delay time is going to be occurring. After that what happened? We are going to be increasing the anode voltage. This voltage is going to be, whenever we fall down from its 90% to 10%, automatically what happened? The space, the region occupied by the anode current to flow through the device is going to be increasing. Okay, that's why we are getting these characteristics. These are the characteristics. After that, we have the spreading time. What does it mean? Spreading time means, so our current flow in the device is going to be spread over the entire device. That is the meaning of it. The time taken by the anode current to spread over the device is nothing but the spreading time, and we can say that is a peak time also. Sometimes peak time also we can mention it. In that condition, what happens? All the maximum, this J2 junction is going to be breaks down and allows the current to flow. And we can say after this rise time means our anode current reaching to 90% of its maximum, but it is not 100%. After that, what happens? It's going to be reaching to maximum value and maintaining the constant value. So this duration is called settling time or spread time. We can call peak time. Different names that we can use. So after that, what happens? This is the value. So here what happened is J2 junction breaks down. Already J1 is already breaks down. J3 is already in the forward bias. So there is no problem with this J1 and J3, but the problem is J2. Now after that rise time, we got the breakdown for this J2 junction. Means there is a charge carriers freely moves from anode to cathode because of J2 junction breakdown. So now what happens? What are the charge carriers? We can say there are the holes in the p-type materials, there are the electrons in the n-type material, and there are some combination of holes and electrons in the J2 junction, because it is only the junction to break down to flow the anode current through the device. That's why there is a combination of holes and electrons between at the J2 junction. So what I am saying is charge carriers. Charge carriers are plays vital role in this operation. So due to that, what happened? Anode current is flows from anode to cathode. So till this period, we can say this is T-on period. T-on period. So T-on period is associated with three timings. One is delay time, second one is rise time, third one is spread time. Spread time, why we are calling that as spread time? Because the current flow in the device must be spread over the entire structure of the device. That's why we are calling that as a spread time. After spreading that current means allowing the current through the device, that what we call our device comes to on state from its forward blocking mode. Device comes to on state from its forward blocking mode. That we can define the turn on timing like this. We can define the turn on time like this. So the instant varying from the device starts to conduct, means coming into conduction state from its blocking state, is nothing but the turn on time. Turn on time is time taken by the SCR to come into conduction state from its forward blocking state. That's what we call turn on time. So after that, we are going to discussing the turn on process of the SCR. For the turn on process of the SCR, so gate signal is not required. So until this period, I am applying gate signal. Until this period, I am applying gate signal. After that, I can remove the gate signal. There is no use of gate signal. And one more thing is that we can switch on the SCR. We can switch on the SCR with the help of gate voltage, but we couldn't switch off the SCR with the help of gate signal. That's why there is no need of gate signal for the further operation. That's why I am removing the gate signal here. Then removing the gate signal here. So till this point, our SCR is in on condition, means conducting state. In the conducting state, what we call SCR? SCR is like a closed switch which allows the current to flow. In case of forward blocking state, what we call that? So SCR acting as a switch in off condition, means it doesn't allow the current to flow. Whatever the voltage applying across the switch across the device and load, the entire voltage is appear across the device itself only. If there is no voltage across the load, we can say. That time what we call, when we apply the KVL to that particular circuit, that series circuit, we can understand very easily. So means what? Whatever the applied voltage is there, that is available across the device when it is acting as a when it is operated in the forward blocking state. So we can say when you use the SCR in case of circuit, in case of switching devices. So in that case, we can say it is the switch. It is acting as a switch in off condition. Actually, we have the two conditions of switches. That is off condition and on condition. When you take the normal switch. So in this case, it is a static switch. We are going to controlling more and more using the SCR as compared to olden switches what we are using in our switch boards. Okay. Now coming to turn on process of the SCR. For the turn on process of SCR, as I said, there is no requirement of gate signal. I just removing the gate signal. Why do you want to waste my supply? That's why I'm removing the gate signal afterwards. Then I would like to bring my SCR into forward blocking condition from its on state from this time. So for that purpose, what I am doing is I am going to apply some commutation methods. Commutation method. The term here commutation. Commutation in case of decimations is a different sensing, and in case of power electronic it gives some other sense. So means what? Commutation in the sense, suppose let us take for example SCR is there. SCR is in on condition. So we have to bring that SCR from its on conditions to the off condition, means forward blocking condition. For that purpose, what we are doing is we are going to apply the commutation process. Commutation process. What we call the what? How do we define the commutation process? Commutation process means to bring the conducting SCR from its conducting state to forward blocking state by reducing the anode currents below the holding current levels. Below the holding current levels. As I said, as I given here, you can see this is the IH, this is the IL. So static characteristics of SCR are associated with two terms. Those are latching current, holding current. Latching current and holding currents are correlated ones, and you can say there is a relation between holding current and latching current. Latching current is always greater than holding current. It is almost 1.5 to 2 times the holding current. Means what? Whenever we are able to reduce this anode current less than this holding current values, automatically the SCR comes back to forward blocking state. Hence SCR we can say acting as a off state condition switch. It doesn't allow current to flow through that device. So that what we are going to see right now. So see here, look at this. This anode current, anode voltage is maintaining the constant values till this point, constant values, and it is zero level. You can say switching voltage drop value, switching voltage drop value. Okay, then you can see when we are applying commutation process to make the SCR, to bring the SCR into off state, forward blocking state, then immediately current flowing through the device SCR is going to be decreasing like this. So after reaching to zero, anode current is totally not flowing through the device and reaching to zero. Look at this. This is time what I call T1. This is time what I call T1, T2, T3, and T4. This is T4. 4 different timings that I have mentioned here. Look at this. At T1, current zero, anode current is going to be zero, and the voltage across device is maintaining the almost negligible value. Voltage not will be there, that I am showing here. So it is maintaining the same value. After that, what happened? Soon after anode current zero, it has to come back to the forward blocking state immediately. That has to be happen in the device. But what happened in this case is it doesn't comes back to forward blocking state. That is the beauty of this SCR operation. Look at this. Why it is happening? As I said, here some charge carriers are there. Charge carriers are there. Topmost layer is P-type material. Topmost layer is P-type material. And what are the charge carriers that we can see in P-type material? So holes are the charge carriers in the P-type material. When you see the bottom layer, this is the N-type material. N-type material having the charge carriers, electrons are the charge carriers in the N-type material. Okay, charge carriers are excess charge carriers are there in the P-type material, outermost P-type material. Excess charge carriers in terms of electrons are there in the outermost N-type materials, and we have the combination of holes and electrons, what we call charge carriers at the J2 junction. So now what is our aim is we have to remove the excess charge carriers at the outermost layers and at the J2 junction. If you remove them immediately, that SCR comes back to forward blocking state. We can bring that SCR back to the forward blocking state. So for that what we have to do? For that what we have to do? To remove the charge carriers at the outermost layers, what we are doing is we are applying the commutation process simply. We are applying the commutation process simply. So for that, in that case what happened? In that case what happened? During the removing of excess charge carriers at the outermost layers, our current after reaching to zero, it is increasing reverse manner. It is increasing reverse manner. It is increasing reverse manner means our current trying to flow in this direction. Our current direction flowing in this direction. In that case, what happened? Because of this current, because of this opposite current, the charge carriers at this and these outermost layers are going to be removed very easily. So we are able to remove the charge carriers at outermost layers by applying the commutation process. But there is a big problem to remove the excess charge carriers at the J2 junction. This is my J2 junction. At this holes and electrons both are there as charge carriers. For that, what we have to do is recombination process. Combination is there earlier. Now what we are doing is recombination process has to be takes place. For that, what we call reverse gate signal. Now initially what I did, I applied forward gate voltage to turn on the SCR. So after that, I removed gate signal, forward gate signal. Then after I applied commutation process to bring back the SCR into blocking state. So I brought the anode current to zero value, but still my SCR doesn't come back to forward blocking state because of excess charge carriers at the outermost layers and at the junction jet. And I applied commutation process to remove the charge carriers at the outermost layers so that those are going to be disappeared afterwards because of the current going in reverse direction. Then what happens? If the current is going in reverse direction means the voltage builds up across the device in reverse manner. Voltage builds up across the device in reverse manner as same as the current. Then what I am doing is to remove the excess charge carriers at the junction J2, I am applying gate signal in reverse direction. Reverse polarity. Negative voltage I can say. When I apply negative voltage through that gate signal, gate terminal, automatically whatever the excess amount of charge carriers at the junction J2 are going to be disappear, can be removed very easily. So for that purpose, what happened is after I am applying gate signal, automatically it is going to be increasing, means decreasing and increasing in forward direction our anode current. After this portion, again our SCR comes to on state, the same thing on timing, whatever the delay, rise time, spread time is there, is repeating again. After this timing, what we call this is the crucial part of the turn off period of the SCR. So this is the main thing. Soon after this anode current reaches to zero, we are saying that our SCR came back to forward blocking state, but it doesn't come back to forward blocking state. After some time, after this thing is happening inside the device, then only it come back to the forward blocking state. So that we have to know in this case. And I can say here turn-off timing is associated with two timings. Look at this. This is the one time that I call reverse recovery time. Reverse recovery time means what? Whatever the charge carriers are, the excess amount of charge carriers are, the device must be removed. For that, the device takes some time. To a time called reverse recovery time. It has to come back into forward blocking state. What we call reverse recovery time. After that, what happened? To To remove the charge carriers at the junction J2, what I am going to applying? Gate signal in reverse direction. Gate signal in reverse direction. What I am calling the gate recovery time. Gate recovery time. So finally, what I am concluding here, the turn-off process is associated with reverse recovery time and gate recovery time. Two factors. And we can able to see two more terms, what I call TQ and TC. TQ and TC. TQ means it is device turn off time. TQ means it is device turn off time. And TC means circuit turn off time. TC means circuit turn off time. Circuit turn off time means, so if we are using our SCR in a particular circuit, so we want to make the current flowing in the circuit into zero. We have to make the entire current in the circuit zero. The time taken to make that current into zero values. What is the time? The time must be greater than the device turn off time. Greater than the device turn off time. Means what? Our device must be turned off first. Thereafter, the entire current, whatever there in the circuit, must be zero. That is the meaning of this circuit turn off and device turn on. So there is one condition that I have written here. So TC, circuit turn off, is always greater than the TQ. If this condition is not satisfied, what will happen? What was the disadvantage for this circuit? Very simple. If the circuit turn off time is not greater than the device turn off time, then mal operation comes into action. Means instead of going for forward blocking state, immediately our SCR comes back to the conducting state, which gives us mal operation, which will damage the entire entire circuit also. So we have to take care about this condition. This condition. Okay. So in this entire diagram, we have seen dynamic characteristics of SCR. We can say some other name for this characteristics, switching characteristics of SCR also we can call that. And continues for this, as I said, turn on, turn off, both are there. Okay. So these are the characteristics, as I said. And what are the turn on methods of SCR? We should know. What are the turn on methods of SCR? And how do we turn off the SCR? What are the commutation methods of SCR? So two things we have to discuss furtherly. So what are those two? Turn on methods of SCR and turn off methods of SCR. Means firing methods of SCR and commutation methods of SCR. We'll see them in the next video. Thank you.